In this video we're looking at translational equilibrium. It's actually going to tie together the free body diagrams from the previous video back with Newton's first and second law as well. So just to explain how this comes about, we're looking now at when the forces, so basically looking at Newton's first law. So when the forces on an object are balanced, and that means we're looking at a situation that's involving Newton's first law, so I'll just make that note. What we would say in that case, we'd say that the object is in translational equilibrium. Now, just to clarify what those words mean, translational basically just means moving. So we're talking about it sort of translating from one point to another, and the idea of equilibrium means that everything is equal. So in this particular case, the forces acting on the object are all equal. Another way to think of that, it's basically tying back to Newton's first law. The translational motion is constant, and there are two specific examples where translational motion can be constant. The first is that it's stationary, so there's no velocity, or the second is that there is constant velocity. So they are the only two scenarios where translational equilibrium occurs. If you have an unbalanced force, so Newton's second law, then you don't have translational equilibrium. Just make another quick note here. I won't write this down, but I'll just mention it. We are talking about translational motion here only. There is another type of equilibrium that we can deal with, and that's rotational equilibrium. So if you're looking at the rotational motion of an object, so rotational equilibrium does exist, but we won't be covering it in this unit. I believe it's part of option B, the engineering physics. But like I say, it won't be covered here, so let's just mention that as in passing. If we think about this scenario though, another way of saying that forces are balanced, so forces on an object I should say, is to consider an equation. Would be so saying that the forces sum to zero. Now this is, you may recall I mentioned in the last video that we'd use the car on a hill example, car parked on a hill. So I want to come back to that one, and just to save a bit of time, we'll just use that same diagram again. So here's the free body diagram that we were looking at in that last video. With this scenario, rather than sort of using all of these labels, let's consider what quantities we'd use. So for the weight of the car, we'd use W. For the force of the road on the car, we'd call that the normal force, so the force that's acting perpendicular to the surface, and the friction between the tyres and the road, we'll just call that the force F. So in this case, actually let's use the subscript F to make it clearer that it's a frictional force. So if we were to consider the mathematical or the equation that we'd write, we'd say that the weight force down plus the normal force plus the frictional force is equal to zero. Which is not too dissimilar to what we talked about with Newton's first law. If we now look at this free body diagram, though, we're going to represent this scenario in a slightly different way, linking in with the subtopic 1.3 on vectors. This representation of the equation, we can represent that graphically as well. So it's sort of like a free body diagram, but not exactly, because the forces won't all be represented as passing through the center of mass of the object. But if we were to consider the weight force, so notice that that vector looks the same as this one over here. We're now going to add to it the normal force, and graphically what that means is that we draw the normal force as starting from the tip of the weight force, and it would be represented, it's a little bit the wrong direction, so that represents the normal force. So basically all I've done is taken this arrow and now we've moved it so that it's in this position instead. Finally, we'd add to that the frictional force, so that's that vector there. And again, just taking this vector and adding it to the end of the normal. And what we can see there is that when they are all added together, the resultant comes, or that there is no resultant force. They all sum to give 0, and so we're back where we started. One last thing in this scenario is that when we go through and start solving some problems, trying to sum forces in that way in 2 dimensions can get very tricky, but we've already seen a technique that we can use in order to make that solution easier. And that technique is to resolve into components. Previously we've seen resolving into, say, vertical and horizontal components when we were looking at projectile motion. Now what we're going to do is resolve into components that are parallel and perpendicular to the road. And so in that case what we're really looking at is this scenario with these vectors. We've already got the frictional force is parallel to the road surface and the normal force is perpendicular, so it's really just the weight force that we need to resolve into components. So if that's our weight force acting down, what we really need to do is break that up into 2 components, one that's going to be parallel to the road surface, so we'll call that W parallel, and the other that's perpendicular, so that will be that one coming down in that direction, and we'll call that W perpendicular, so just a little perpendicular symbol. So there's the 2 components. Now resolving basically just means we need to take that, or look at the relationship between the different sides, so we'd need to have an angle in there, and let's say we're using this one here. If we use geometry, we could show that that angle there is actually equal to the slope, the angle of incline of the slope itself. We can have a look at that in class in a bit more detail. But ultimately, if we were to look at the parallel component, in this case that is going to be equal to the weight force multiplied by sine theta, and the perpendicular component will be equal to the weight force cos theta. So if we then considered the perpendicular components that are acting on the car, we have an equation there that we can consider being the perpendicular component of the weight force plus the normal force is equal to 0. And then if we look parallel, we would have that the parallel component of the weight force plus the frictional force is equal to 0 as well. So there's no motion vertically, no motion parallel to the road or perpendicular to the road, so the components in those directions will sum to 0 as well. That will make it a lot easier to solve some problems involving, say, forces on an incline, or if you've got another example of something like a sign that's hanging with a couple of wires that are attaching it to an awning. So you've got components of tension and the weight of the sign as well. So by resolving into components, it makes it much easier to calculate, say, the tension in those strings or whatever the unknown quantities are. We'll have a look at a few of those sorts of questions in class to help you make sense of the mathematical solution as well as having a good understanding of these concepts.